Good morning, students. Still in Unit 7. Of course, we only did one lesson so far. We had done the second fundamental theorem of calculus, which was a lot of fun. But with day 62, you are going to be able to take integrals of functions and that you could not have done before. You don't even know that you couldn't have done everything by hand. You think you can do every integral by hand because we had given you ones that were doable. But today you'll find out there's more to the story. Okay? It's like Paul Harvey used to say. And now for the rest of the story. And pay attention here. We're really almost done here. I definitely might be not covering so much the slope fields and the differential equations, even though we've done a little bit of diffie-q. But since the AP is not putting in the test, I'm going to save that for the end. And then I got to do areas and volumes. Okay? There's 2 sets of volumes. So we're almost done. Technically, 3-4 lessons, we're done. Okay? But back to the rest of the story of integration by substitution. In the past, we have integrated f of x, taking the antiderivative with respect to x, and generically would say, magically the answer is, well, this is f prime, so if I integrate f prime, I'm going to get f of x plus some constant. This was true because whatever function I was using, I had to have the derivative of some sort of function that's inside f, or f prime in this case. And when I say inside, if I was looking at the square root of x squared plus 1, perhaps the insides was x squared plus 1. If I was doing sine of x, let me do sine of 3x minus 2, maybe the insides is just 3x minus 2. These are your composite functions. F of g of x. You've done this before, mostly in your pre-cal class. And you did it when we had to do the chain rule. Remember? We had to do it with the chain rule. And since integration is the opposite of taking the derivatives, well, now we're doing the opposite of functions that you would had to have done chain rule in order to have had that function we're taking the antiderivative of. So right here, we're going to start out with the function, f of x, sine of 3x. Obviously, it's a candidate of chain rule. So, and look at, they're even calling it integration of composite functions. We have not done that. So f prime of x in this case, would be the derivative of the insides, and that's the inside function, times the derivative of the whole thing. So we did it this way. We did derivative of sine is cosine. We kept the argument. And now I do the derivative of the argument times 3. Do the second one while I'm here. If you look at e to something, we always called it e to the u du. E to the u. And to do that derivative, f prime of x was e to the u, e to the cosine of x, times du, the derivative of the function. That would be a negative sine of x. So if I'm now integrating the f prime, and I'm integrating cosine of 3x times the 3, and don't forget that we make that integral sandwich, you should not be surprised that the answer has to be exactly what we started out with. Whoop. Over here. If we undo the derivative by integrating it, you should not be surprised that the answer has to come back to the original problem. Sine of 3x. Of course, plus some constant. So take a look and say, well, how did all of this, why did I not factor out the 3 like I've done in the past? It's because we had a compound function. That 3 was needed to be next to the dx, because if you were to do the derivative of sine of u, the answer was cosine of u. Remember the derivative, cosine of u du, chain rule. The u du has to go together. That is why the 3 dx does not factor out. It goes away because it's part of my differential. Okay, let's look at the next one. You should not be surprised that if I integrate e to the cosine of x sine of x dx, remember the integral sandwich, since you know you just took a function, took the derivative of it, now we're undoing the derivative, you should just say to me the answer was the original function, e to the cosine of x plus c. And why is that true? Because sine of x dx was my du. My du, if this was my u, this is my du. And this is why often we call this method integration with substitution, because we're substituting cosine of something as a u. And then I had to ensure that I had the du. If you don't have the du, if I was just to give you the problem, integrate cosine of 3x dx, at this moment, you could not integrate that because you're missing the du. And du has to be the inner function. U would have to have been 3x. Du would have to be 3 dx, which was not there. We can fix this one. Don't fear. We still could do this problem. We would just have to play magic and say, well, what if I multiplied this by a 3? Is that legal? It certainly is, as long as I counterbalance it by dividing the whole thing by 3. And now what you have is, this still goes away. But at least I have the u du, so the answer now will be 1/3 of sine of 3x plus c, as opposed to just sine of 3x plus c that I had before. Because I already had the 3 built in. This one did not have the 3 built in, so I added it and I canceled it out over here because 1/3 times 3 is 1. It doesn't change the problem. It's the same thing with the second problem I did. If all I had given you was integrate e to the cosine of x dx, you could not have done this problem by hand. I can't even create the du. If u equals cosine of x, I need to have the du, which would have been the negative sine of x. I don't have it. I just didn't have it there. So this would not be doable with my U substitution. And I was just thinking about this problem. Oh, I had a negative. I was worried. I didn't remember if I had my negative here, because if that wasn't there, I would have had to have fixed the problem. I don't think I wrote it down over here, though. I should have written it negative over here. And then it all works out beautifully. I just caught my own error here, that it would have had to have had the negative, and I just didn't have it. Okay, so I've given you a lot of information right now. The first page was just to say, hey, common sense. If you take the derivative of this problem, then f prime of x would have to have been 4, keep the insides, do the derivative of the insides, 4x, easy peasy. I should start calling this a u. 4 times u times du. I should start doing that, really, when I teach this stuff. And then, using common sense, if I integrate my 4 times 2x squared plus 3 times 4x. Oh, I missed something, didn't I? Where'd my exponent go? Forgot to write it. 3. That's what I'm... Because everything is there that I need, my du is there, it's not a surprise that the answer comes back to the original problem, which was 2x plus 2x squared. Did I do my du right? Yeah, I did. 2x squared plus 3. All to the 4th power. It makes a lot of sense here. Now you might be wondering, would I have pulled out the 4? Probably, but you're going to be dividing by a 4 anyway, because that's the 4th power, so it's going to cancel it out anyway. Okay, one more here. So here's my u, square root of u. Should not be a surprise that the derivative will be u, which is x squared plus 3, and raise that power up to 3/2. I'm wrong. Take 1 away, not add 1. What was I? Negative half, and divide by negative half, which means negative 1 over 2, so negative 2 is there, times the derivative of the inside, 2x. So naturally, without even going into any of the detail, if I integrate all of this problem, 2 over the square root of x squared plus 3 times 2x dx, and it doesn't matter what form you put it in. I'm not going to multiply the 2 times the 2, because I truly do want you to realize that this is u du, and you can't integrate unless you have u du. So if my u is in here somewhere, right here, my u, if u is x squared plus, can't read my writing anymore, 3, that was a 3 here, a terrible 3, x squared plus 3, then I have to look for a du, which is a 2x dx. There it is. So it's not a surprise that that answer has to be the original problem, which was the square root of, original problem was square root of x squared plus 3. without overthinking it. I actually talked way too much about these problems. So pattern recognition. In terms of composite functions, when you do the derivative of f, and this is my u, we remember that the answer was f prime, keep the insides, times the derivative of the insides. Now you should have seen that when I do my f prime of g of x, I needed to have the g prime of the, this is the same thing as me saying u du. Since it's there, then the answer will just be f of x. I'm sorry, I should say, wasn't an x in there, was it? F of g of x plus some constant. That's just because this was connected to the problem. So I'm looking at this problem, and we're looking for pattern recognition. So he wants us to identify what my f of g of x is. And so I'm looking here, and I see cosine of 3x. So my big function is cosine. My inner function, g of x, would be just 3x. So I'm truly looking at integrate f of g of x. F of g of x, cosine of 3x. But what do I have to have next to it? I need to have my g prime. So when you identify the inside function as g of x, or u is 3x, we have to ensure that g prime of x, or du, I like to call it, would be a 3 dx. Because the derivative of 3x is 3 with respect to x, 3 dx. I know what you're thinking, it's a 1, but yes, but this is, you're taught, you still got to keep the differential in there. I mean, to remind you. Well, I won't go into that. So I have to look at my problem. Do I have a 3 dx there? And I do. So since my du is there, then the final answer has to be the integral of 3 cosine of 3x dx must just simply be the antiderivative of cosine of 3x, which was sine of 3x. Okay, so we just say the big function is f, so the derivative of cosine is, sine was cosine, or the integral of cosine is sine, positive, and it had the argument originally of 3x. Okay, pattern recognition. I'm going to change it to u and du only because that's pretty typical. I like his style of f of g of x because it does play home that it's composite functions. I do like it, but so I'm looking here, and I got to identify something in this problem to be u, and u always has to be the inside function. So u has to be whatever is embedded into the original. So it would make sense to say that u is equal to x squared plus 5. And du would have to be a 2x, and what respect to what? With respect to x. So I am looking here, and I see a 2, and I see an x, and I see a dx. So if it's all there, then it's sort of like rewriting the problem like this. I have a u to the 1/3, and all of this is du. And if I was integrating all of this, my answer has to be a u to the 4/3 divided by 4/3 plus c. But since my function is in terms of x, I need to substitute back the correct notation. It's 3 and 4/3 power. I'll just leave it as 4/3. I could say 4th root of my u, which is x squared plus 5 over the 4 plus c. But most of us would have just said 3 times x squared plus 5 to the 4/3 power plus c. You got to do about 100 of these and you'll feel good. I'm serious. So now this is a composite function. It's not just simply the cosine of all this or the negative cosine of all this. You have to look carefully and say, there's my inside function. U must be 2x plus 3. So in order to do this problem, du would be a 2 dx. And lo and behold, there it all is. So these two, some people rewrite the problem and just say, integrate sine of 2x plus 3 times my 2 dx. And they realize that the integral and the 2 dx go together and they disappear. It's just there so that I could do the integral, the antiderivative of sine, which is a negative cosine of 2x plus 3. Here's how that works with u. See, it would be integrate sine of u du. The answer is negative cosine of u plus c. Negative cosine of u. You see that? Okay. You got to just do a lot of these. You really should be asking me, sir, can you give me a whole bunch of these problems for practice? I got a whole bunch. Now this looks very complicated. It's really hard to see what u is when it's a rational function. But I'll give you a hint. We love u in the denominator. We love it, love it, love it. Because if u is in the denominator, I'm going to pray that du is in the numerator. Look what's going to happen. I'm going to try it out. Sometimes we try it out and it doesn't work. So we have to try a new method. You could do this problem with other methods, probably. You could use partial fractions. That's in Calculus BC. You could use a TI Inspire, which will integrate it with the plus c. But anyway, let u, I'm going to just try this out. Sometimes I'm wrong. Let u be my denominator. Then du must be 2x plus 2 dx. And my heart does a backflip. Gets really excited. Because look what I see on top. Do you know what I'm looking at? I'm looking at a du over u. We love du over u. Where does a du over u come from? Remember when I was taking the derivative with respect to x of natural log of x? It's du over u, derivative of this 1 over itself. Remember when I did the derivative with respect to x of the natural log of 2x squared minus 5x? That was du over u. 4x plus 5 over the 2x squared plus 5x. Remember that? Well, that's the same thing that's happening here. I'm looking at something that was a natural log, because that answer is natural log of u. I know what u is. So this answer is natural log of x squared plus 2x. And I am going to tell you, since you can't take the natural log of a negative number, we like to put absolute values on our natural logs. Wow, that was fun. I know you're having fun too. Okay, let's see. Let u equal to 3x plus 2. Then du would have to be the derivative of this, which is 3 with respect to x. And I'm so sad. I'm brokenhearted. All I have is a dx and the integral. What am I missing? You're right. I'm missing the 3. So what I do with this problem, I say cosine of 3x plus 2. I was missing the 3, so I add it. And to cancel that operation out, I multiply the whole thing by 1/3. So now this integral and this du all goes away. So what I'm really looking at is a 1/3 integrate cosine of u du. If that's really what I'm looking at, then the answer is 1/3 integral of cosine is sine of u plus c. But we need to resubstitute back in. So I'll leave it as 1/3 sine of 3x plus 2 plus my constant. So from now on, whenever you integrate, always think u du. Even if it's a basic problem, ask yourself first, is du present? Okay. So u inside function x squared plus 2. Outside function was the square root, so that's what's there. This is my inside. Du would have to be 2x dx. Oh man, I'm so close. Because look what I have. I have a 3x dx. Well, you know what? That 3 is not helping me at all. So let me pull the 3 out and call it a square root of x squared plus 2 with my x dx. All I did is pull that 3 out. It wasn't helping me a bit. What's missing? The 2. Cancel it out. So now what happened is I'm integrating something with a du in there. So it's 3/2 integrate u to the 1/2 du. Obviously, that answer has to be 3/2 u to the 3/2, because I add 1 to the half, 3/2, and I divide by 3/2, 3/2 plus c. Now that's just a big mess, because 3/2 with a 2 up there and another 2 down here, look at all that multiplying. I hope you see that 3/2 times 2/3 just cancels out. This gives me 6, this gives me 6, it cancels out. So you're really looking at a u to the 3/2, and u was labeled up here as x squared plus 2 to the 3/2 plus c. It actually is simpler than it looks, but it won't feel that to you. I'm just old and done this a lot. Now, maybe that 5 is important, maybe that 5 is not. You lose nothing if you just randomly say, okay, let me pull it out. Then you might say, why did I pull it out? I needed it. But let's see what happens. U must be 2x. I'm sorry, 3x. Then du has to be 3dx. Well, I was right. That 5 wasn't helping me anyway. Because I got to multiply by a 3 and cancel it out. So I'm looking at the real problem is 5/3 integrate e to the u du. Which is really kind of simple because whenever you integrate e to the u, the answer is e to the u. So my final answer is 5/3 e to the u plus c. And go ahead, substitute my x material back. U is 3x, so 5/3 e to the 3x plus c. I see a rational problem again, rational function. So I'm thinking u should be in the bottom and du should be on top. At least that's what I'm praying for. So let me see if it's going to work. Let u equal to 2x squared plus 3, and du should be 4x dx. Well, it's almost there. The 3 doesn't really need to be there, but I need to add a 4. So I'm really integrating. The 3 comes out. There's my x, and there's my dx, and there's my square root of 2x squared plus 3. And what I will be doing is getting that 4 there. So a 4 is going to go here, and a 4 is going to go here. But to me, that looks very cluttered. So I'm going to rewrite it as equals to 3 integrate du over u. And don't forget, in order to have my du, I had to multiply by a 4. And then there's my cancel out my 4. And there's my du. Integrating with respect to u, there's my du. Final answer, 3/4 natural log of square root of 2x squared plus 3 plus c. Can somebody tell me why I don't need to use absolute value? You're right. Square root is always positive. Boy, that was fun. He just continues this idea. Let's fill in some blanks. In each of the 8 examples above, the ones we just did, the g prime of x was a license to integrate. Oh, I love that. Existed in the integrand of the integral of f of x of g f prime of x g of x times g prime of x or g prime of x was obtainable by multiplying by a constant. I need to star this because that's the only thing you're allowed to do is multiply by a constant. You can't multiply by a function. The g prime of x does not always exist, and there are more times than not that it is not obtainable by multiplication by a constant. So it happens where you can't fix it. Consider this example. Okay, so let's see what happens here. Identify the inner function gx. I'll identify it as 2x minus 1. So what's the derivative of this? What would I have to have? If this is my u, what's my du? I would need a 2 dx. Well, look up here. I have my dx. That doesn't look like a 2. So guess what? I can't At this point, I don't have what it takes. Okay, let's see what he says about this. Is g prime of x part of the integrand? No, it's not. Because I have an x dx, and what I wanted was a 2 dx. This is what I wanted, and that's not there. Is g prime of x obtainable by multiplying the integrand by a constant? Constant means number. Is there a number that I could multiply inside to make that x turn into a 3? All right, don't tell me I could multiply by 3 over x, because that would have worked, but that's not a constant. That doesn't work. So the answer is no. In this case, we must find the antiderivative by a method known as the U substitution. All right, so what he's saying to you is, even though I have been calling it U substitution from the beginning, some people don't call it U substitution until you really, really, really have an issue. You just look for the G of x and G prime of x and don't even think about U's. But I called it U's before, so let's go through with his method here. Let U be the inner function. That's what I was doing. Okay. Let U equal to 2x. Was it minus 1? Minus 1. That's fine. That's a step. That's my step 2. Step 2. Find the du. Okay, then du, I already did it, was 2 dx. But look what he said. Find du and solve it for dx. He went one step further because it was obvious that I didn't have a u du in there and I couldn't make it. Since I couldn't make it, we have to go a step further. We're going to turn this whole equation into nothing but u's and du's, but I can't right now because of the extra x. So why don't I take this du is 2 dx and solve it for dx then? And I find out that dx is really equal to du over 2. Okay? Now, find an expression for x in terms of u. What do you mean, expression for x in terms of u? Go back to your original problem. If you recall, u was equal to 2x minus 1. Let's solve this for x. So if I solve it for x, u plus 1 equals to 2x. X is equal to u plus 1 divided by 2. So now, my dx is in terms of u. My x is in terms of u. This is where it gets sticky. Rewrite the entire integrand as a polynomial or polynomial type in terms of u. So now I want to rewrite this whole thing, just like I did before with u and du. But this time I had to be very creative. I had to work a little harder. So let me take my original problem. I'm integrating. It was integrating x times 2x minus 1 to the third power dx. Now watch what I'm going to do. What's another name for x? Go down here. X was u plus 1 over 2. That goes here. So I'm integrating u. What am I writing 2 for? U plus 1 over 2. There's my x. What's another name for 2x minus 1? Well, remember, 2x minus 1 is a u. U to the third power. What's another name for dx? Here you go. Dx is, it goes here, so dx, I don't want to put, let me erase that. I don't want to put all that there. Whoop. Let me write it, like put it on top. There. Du over 2. Now, just clean this up. Just clean this up. I forgot my cube here, didn't I? No, wait. No, this was cubed. Not this. What am I doing here? That was my x there. This is my there. Now it looks good. So I'm going to distribute my u cubed inside. So I'm integrating u to the 4th plus u cubed, and this is a 2 times a 2. So really the whole thing is divided by a 4 du. That 4 doesn't help me. So I can just pull that 4 out as 1/4. Now I'm integrating u to the 4th plus u cubed du. Integrate each of these separately. That gives me 1/4 u to the 5 over 5 plus u to the 4 over 4 plus c. Aren't you happy? But what was u? We have to put the x's back in. U was equal to 2x plus 1. Put it back in. 1/4 times 2x plus 1 over 5 plus 2x plus 1 to the 4th over 4 plus c. Could you clean it up more? Where's my 5 at? 5 over 5. 2x plus 1 to the 5th over 5. Yes, okay. You could expand it and make it prettier. You could even, I just, if you want to put the 4 back in and call that a 20 and call that a 16, that works for me too. Wow. I may redo this one on my own just to make sure that it looks good. Okay. I have a feeling it's another ugly problem. If I had to call it, I'd be wanting my u to be in the bottom. So I'd want u to be x plus 4. And du would have to be a dx. Well, guess what? I have a dx. But what is all this garbage? It's extra stuff that I don't need. I'd be okay if I didn't have all that. I could integrate if it was just 1 over the square root of x plus 4 dx. I could do that, but I can't do all that. So here it goes. This is a job for the complete U substitution. What's my inner function? I said it was x plus 4. So u, well, he wants me just to identify, yeah, u equals to x plus 4. Then he wants me to figure out and solve an equation for dx. Well, if u equals 2x plus 4, then du must be equal to dx. Well, that's not very exciting. Now I got to write the whole thing with terms of u's and du's. So let me write it out. It was 2x plus 1 on top. So I'm integrating 2x plus 1 on top and a square root of x plus 4, square root of x plus 4 dx. So let's see how hard this is going to be. Equals to my x. Did I ever solve for x? I never solved for x. I didn't solve for x up here like he made us do in the past. X will be equal to u minus 4. That's very important. You need to have that. So we got two equations. We got our x solved for and we got our dx solved for. So x is u minus 4. 2 integrate 2 times u minus 4 plus the 1 all over u to the 1/2. And dx is du. So if I clean that up a little bit before I go to the next part, let's try to clean it up. Integrate 2u, and remember what I had. It was a u plus 4 up here. Remember? The x was a u minus 4. So I had a 2u minus 8 plus the 1 over u to the 1/2 du. Let's go ahead and keep finishing it over here. I'm integrating 2u minus 7 all over u to the 1/2 du. Now that may not look fun for you. How would I work on that one? I probably would break that up into two fractions. 2u over u to the 1/2 minus the integral, and both of these will share the du. You can put them together if you want. 7 over u to the 1/2. And then that was sharing the du. Well, it isn't too bad because that simplifies into u to the 1 over u to the 1/2 really becomes 2 u to the 1/2 du. This one really becomes 2u to the negative 1/2. So it really works out pretty simplistic. Both 2's are in the way. So technically, I can take that 2 out and just say, what's the integral of u to the 1/2? U to the 3/2 over 3/2 minus, what's a negative 1/2 plus 1? It's a 1/2, so that becomes minus 2 u to the 1/2 over, divide by 1/2, 1/2 plus c. So it's coming together really well. 4/3 u to the 3/2 minus a 4 u to the 1/2. And that's pretty simplistic, except for I don't want u's in there. So go back to the left here. What was another name for u? You found it. X plus 4. This goes back in now. Assuming I made no stupid mistakes, which I'll never guarantee it, I'll have 4/3 times, what I say, x plus 4, x plus 4 to the 3/2 minus 4 times x plus 4. I was going to put square root, but I'll just keep it consistent. That's cool. They do not get harder than this problem in calculus AB. They just never do. You just don't have time to do one of these problems on a free response problem. So you'll never really have to do this. But this is your college calculus. Yeah, this is what they expect you to do. The AP, they're not going to give you anything that hard. This was a lot. I just hope it's correct. And, oh, I'm done. You know what I'm going to do? I'm going to post this early because I think you're going to need to watch this video twice. Practice them on your own. I would do every problem over again all by yourself before you even attempt the homework. How many do you got here? You got 6, 7, 8, 9, 10, 11, 12 to play with. Happy integrating. Peace be out. And then there's some multiple choice. Oh, yay, multiple choice questions. So 3 more. AP exam. This one, actually, you work it out all the way to get an answer. This one, you're just setting it up. Look at that. You're just setting it up. You're not even really doing it. You're just showing it you know what U substitution is. Look at this one. This one is that differential equation that we've had in the past. You would have to basically solve that. Let's see. I need y's to go with my dy's and my dx's to go with my x's. So you would rewrite that into y dy equals to x squared dx. And then in this case, if you integrate both sides, that gets rid of the differentials. And the y is with the dy for a reason, because if this is my u, this is my du. Now this is my u, that's my du. So this turns into y squared over 2 plus a constant, I'll call it constant 1, equals to x to the 3 over 3 plus a different constant. But if you think about it, you move this constant over and combine them, you just get another constant. So instead of saying y squared over 2 equals to x cubed over 3 plus a third constant, you just pretend that the whole time there was just one constant. You worry about constant one time. So there is a perfect equation. Now, he gave me an initial condition. So you would have to plug in this equation. This is my x, this is my y, to really see what this equation is. So my y was a -4, -4 squared over 2, and my x was a 0. So what is 0 cubed over 3? 0. There's my constant. My constant of integration is a 16 over 2 is 8. So what my equation really is, y squared over 2 equals to x cubed over 3 plus 8. But it's not an equation until you solve it for y. So I will leave the rest up to you. In the next page, 4, 5, 6. Well, look how they are on more problems. These are really good. And so 1, 2, 3. Nope, that's new lesson.